hopefully I put something in here as a little bit for everyone. So, go. All right. So, welcome back from lunch. As you've heard several times, my name is Chris Simmons. I'm from the University of Texas at Dallas. I have a dual appointment. I'm director of the Cyber Infrastructure Researcher Support, and I also hold a faculty position in computer science, where I teach programming, high-performance computing, and things of that nature. So, like any good academic, I came yesterday and showed up late and hadn't prepared my talk at all. And I kept my talk title very vague. And Henry wouldn't accept things that Chris wants to talk about as the title of my talk. So listening to everyone in the meeting and how it's progressed, and I hear people talk a lot about software in terms of support headaches, or how do I choose a good software tool, or why the hell do I have to compile this crappy code? I thought I would write a talk from that point of view, talk about what the problem is, and I'm not going to tell you how to find a great code quickly, but I'm going to tell you quickly how to identify red flags. All right? So the title of my talk is Mapping Research Requirements to Software Tools. So what's the problem? Why is this hard? Well, I guess I can't use the laser.
It is not the laser.
I would say that's encouraging.
Oh, there is a laser. I see the laser.
Yeah, see the laser. Anyway.
The people in TV land won't see the laser.
That is true. So computer science software is not well funded. Typically funding agencies fund science, not software. This has changed a little bit, especially with like the NSF SI2 program, which I participated in 3.5 times. Yes?
What does SI2 stand for?
Oh, Software Institute or Scientific Software Institutes. And these are for specifically NSF funded programs to catalyze community codes or to further support community code development. So I was in some SI2s in both developing of solvers and in developing codes for electronic structure theory. Computational science software complexity is constantly increasing. Every time someone gets a PhD, it becomes that much harder for the next person to get a PhD. So the fence is constantly moving. So the next person to get a degree in that field has to go a little bit further. Experimentation is getting cut all over the place, but computation is increasing everywhere. And several companies and government agencies are replacing experimentation and even initial design phases with pure computation. So the applicability is ever increasing. You know, we like to fall back on Occam's razor, right? The simplest answer is probably the best one. But in scientific software, that rarely applies. Mencken's razor. H.L. Mencken was a journalist and satirist in the 40s. If he were alive today, he would either work at the New Yorker or be. And he said, for every complex problem, there's an answer that is clear, simple, and wrong. And the theme of this talk, I'm going to posit that developing your own software to implement every feature you need is perhaps clear, simple, and wrong. It's weird in scientific software that we reinvent the wheel. Right? Isaac Newton famously said, 1676, if I have seen further, it is by standing on the shoulders of giants. However, in scientific software, everyone thinks they're a beautiful, unique flower. Right? I tell my students the same thing I tell my kids. You are not a beautiful, unique flower. Goes over better with my students than my kids. But the point is, for every problem you want to solve, there's probably 100 people who have tried, at least 10 people have written something to do it, and maybe one of them is good. So by standing on the shoulders of software giants, you can hopefully see further quicker and focus more on your science than your software. Now, how do you identify software giants? It's hard. It's very hard. But by listing the requirements of a healthy software ecosystem, I hope to empower you with the tools to let you eliminate some software immediately. And I hope by giving you a process and tools to help increase confidence in someone else's code, that I hope to help you identify good software. And so another quote, being able to quickly evaluate good scientific software is increasingly important. And that's by me just now. All right, so what are my goals for this talk? Or another way of thinking about it, what is the outline? By the end of this talk, you should have a strategy for identifying whether software is worth evaluating. A game plan for building confidence in that software. By the end of this talk, you should have a strategy for identifying what needs to be done before writing your own software or supporting a researcher who writes your own software. By the end of this talk, you should have a game plan for writing your own software. And by the end of this talk, you will have heard generally accepted recommendations on scientific software, as well as several of my highly opinionated ones. I'm very opinionated, as you guys might have noticed in the last 24 hours. Through undergrad, I supported myself doing both lab research as well as sysadmin on big iron machines, Unix. This was in the early 90s. As of 97, I started working on my PhD in computational quantum mechanics. And I've been doing HPC research, high performance computing, engineering, uncertainty quantification, and basically running my own research group for 10 years on fully soft money. And then something happened in Washington and the government cut all my money. So now I'm faculty, tenure track faculty and full-time staff at UT Dallas. So that's sort of where I'm coming. My background is in C, C++, Fortran, high performance computing. But, so, is this talk for you? Yes. If you are a student or a developer, this gives you means to identify software, and if you have to write your own software, how to go about coming up with a plan. If you work in an HPC center, and someone asks you to install software, it gives you the tools to decide whether it's worth your time to support or not. How many times have you guys been asked to support software, you download it, and it doesn't work? There's no build system, there's no documentation. It compiles, but it gives a seg fault. All of these happen all the time. And the second part of this talk, where I'm talking about the tools and the processes to build a healthy open source software ecosystem, for your scientists, your software developer, your students, it's clearly applicability. For those of you who are doing support, this gives you an idea of the software you need to install and the services you need to provide to encourage software excellence. All right. So the first thing you do when you look at a code is make sure it's been version controlled, right? We laugh about that as a requirement, but you'd be surprised how many people do not use version control. And even as a sysadmin, there's tons of sysadmins who do not use version control. Change that. Use version control. If you have text-based files in your life and you're not using version control, you're doing it wrong. So version control is not hard. Web designers do it. My 12-year-old son started to do it. He's now 16 and contributes on GitHub. But when he was 12, he was doing his math homework in LaTeX and keeping it under version control. The standard convention for version control, using a consistent project structure, commit often in logical chunks, write meaningful commit messages. By looking at someone's version control history, you can learn a lot about the quality of the project. First, if they have a version control system, that's a good start. But look through their VC history and see what they're doing. These days, there's 3 version control systems, but as Henry was talking about earlier when he was talking about hydrogen, helium, and everything else, there's Git, and then there's everything else. Now, Git has pretty much won the version control battle. Is it the best tool? I would argue no. I would argue it depends. And I would argue for at least 2 to 3 sigma of projects, it's overkill. However, Git has won mindshare. Git has won mindshare because of GitHub, and it's funny that a distributed version control system has won because of someone providing a centralized service, but that's another discussion altogether. Build systems. If a code does not have a way to reproducibly build itself, how do you have any confidence in it? Now, for a lot of people, a build system is nothing more than a bash script. And that's bad. That's not portable. That's not going to work on multiple systems. A good start is a makefile. However, if you look at a makefile and it has hard-coded paths, share, apps, user, group, my name, etc., again, they're not testing it on multiple systems. It's not portable. So you want to look at your build system and see if they've considered portability. The next step beyond static makefiles is host-specific makefiles. And this you'll see a lot of that people stop with. Makefile.stampede2, makefile.lonestar5, makefile.common, makefile.this, makefile.linux. And that's okay, especially if you happen to have access to one of those XC resources in which they built that for, but it's not ideal. Ideally, you want a proper build system that is cross-platform, supports dependencies, automatically finds include files in libraries, and supports parallel builds. And at this point, that pretty much means you want the auto-splat ecosystem, auto-conf, or auto-make, right? How many of you done /configure, make check, make install? Yeah. How many of you skip the make check step? That's the most important step. If you've done that, you've used auto-conf. CMake is another very popular build system, and CMake and auto-conf are very similar. They're both meta build systems, right? Makefiles are for building code, right? And auto-conf and CMake are for writing makefiles that didn't build code, right? It was meta before meta was cool. Either of those are both high quality. I particularly like the auto-conf family because that's what I learned first. CMake has some advantages and disadvantages. CMake out of the box works better with Fortran modules. CMake also builds Windows binaries, but why would you want to do that? And another popular build system, which is actually pretty cool, is scons or scons. And it actually writes Python files. So instead of having to learn a new language, or in the case of AutoConf and AutoMake, having to learn 4 new languages, all you do is write a Python script, and it builds it. So those are alternative build systems that you could look at. Documentation. This is another signal or another red flag as to whether you want to use something or not. To me, the minimal acceptable documentation is a README file, commented source files, a bugs and a to-do list, and a change log. High-quality codes will have a lot more than that. They'll have model documentations. They'll have a discretization documentation. They'll have code verification plan. They'll have requirements documentation. They'll have automatically generated technical documentation and code structure from commented source files, like Oxygen, right? And they'll have issue tracking. If you find a source code or a scientific software that allows you to submit bugs, that means the person who's making it wants to hear from you. That means they're likely to take feedback. So that's a good thing. All right. Now, as domain sciences become more prevalent, this becomes a little fuzzy. But historically, scientific computing has to be right. And by right, I mean quantifiably wrong. Right? Every time we take something from a continuous representation and map it to a discrete representation to solve on a computer, it's wrong. Every problem we solve on a computer that's not symbolic manipulation is wrong. But you should know how wrong it is. So our scientific programs, you have to have an idea of how wrong they are. For the most part, you want it to be fast. SUs are hard to come by. XC proposals these days can be 15 pages to get a couple 100,000 SUs.
What's an SU?
Service unit.
What does that mean?
So one SU is 1 hour of compute time, or 1 hour of node time on an HPC system. So if a TAC node has 24 cores, 1 SU gives you 24 cores for 1 hour. Right? And you typically get SUs through XSeed in 10,000 to 100,000 increments. And so if your code can be easily made 25, 50% faster, that's a lot of money you're leaving on the table, or a lot of wasted service units. Typically, your code doesn't have to be easy to use, and it doesn't have to be pretty for your high-end users. There's some exceptions with the interfacing with the domain sciences, but for this talk, I'm going to posit that as true. Other types of computing, errors are tolerable, right? Someone mentioned Fortnite earlier. Right? It doesn't matter if the pixel is slightly off, right? It just has to be fast, right? That's why in games, in pixel and voxel calculations, they do it single precision, right? Sometimes they even do it in half precision. Web browsers and email clients don't have to be real time, and usability is very important. Testing. If a code comes with no tests, how do you know it's right? You don't. There are two major branches of tests: unit testing and regression testing, or system testing, or integrated tests. A unit test is a test that tests a unit of source code, and a unit is the smallest possible of test code, right? Smallest possible atomic unit. And typically, if you're writing unit tests, you write the unit or the code under test, the CUT, and the unit test at the same time. Regression tests are larger scale tests, example applications, benchmark problems, and those you want to use to catch unintended consequences of revisions. And a lot of these topics I'm covering, especially testing, I could talk about for multiple classes. In fact, for testing, I could talk about an entire semester on verification. Just be aware that if you download a piece of code and there's no tests, you should be skeptical and scared and frightened. Why test? Right? Scientists don't make mistakes. You might remember a couple years ago, there was a published paper in a non-peer-reviewed journal by a Harvard economist who said our main result is that whereas the link between growth and debt seems relatively weak at normal debt levels, median growth rates for countries with public debt over roughly 90% of GDP are about 1% lower than other ones. And a lot of countries and a lot of economies make decisions based on this non-peer-reviewed paper. Turns out there was an Excel error. And instead of averaging 49 in column L, they did 30 to 44. When it was corrected, it actually showed there was a growth of 2.2%. And then you might have remembered something happened in Greece. This is not an isolated incident. JP Morgan has lost $6 billion at least due to problems in a spreadsheet. Mars Surveyor, do you remember that? Lockheed Martin worked in English units, and NASA worked in metric units, and it perfectly arrived at Mars only to accelerate through it. There's been problems with oil spills, and you might have remembered the 90s, right, when war was first televised. The Patriot missile timings were only off by 1/3 of a second. Turns out that's a lot when you're traveling at supersonic and hypersonic velocities. All right, so in verification, there are two major classifications. There's code verification and solution verification. Now, code verification is fairly typical. It's in every type of code, every type of software. And code verification is basically making sure your code does what you want it to do. Right? In terms of scientific simulations, it's ensuring that the code used in the simulation correctly implements the correct numerical discretization of the model. Right? But if I click this checkbox, it clicks the checkbox. If I sort by weight, it sorts by weight, whatever. Solution verification is not present in all fields, but in solution verification, remember we talked about the discretization error? This is making sure that all the errors from numerical discretization is sufficiently small. What's sufficiently small? It depends. 10 to the -16? That's really small. Is it ever going to be that small? No. It's going to be larger than that, and oftentimes disturbingly larger than that. I'll talk about that a little bit later.
Question.
Yes,
When you say 10 to the negative 16, do you mean absolute error or relative error?
either. Both are really hard. And when I actually talk about verification, I'll show you an example at O0 where you can't even get. Relative error, much less absolute error. On most software, we consider ourselves with relative error, not absolute error. And for most software, if it's in the neg 14, neg 15 range, we're usually happy, especially as you start to get to very large parallel calculations. Your order of operation round-off error starts accumulating at a rate that's higher than your discretization error. So we tend to say, if it's below neg 12, neg 13, I'm usually happy with it. All right, now, how do we verify codes? Or how do we find bugs in codes? That's another way to approach it, right? Well, it would be nice if we had an exact solution to every problem. How many problems do we implement in software that's been discretized that we have an exact analytical solution for? Another way of thinking about it, if there's a problem that has an analytical solution, any problem, do you think someone's already gotten a PhD for it? Yes. Almost every problem that has a closed form solution has been solved, and solved many years ago. Right? So it's very often that you can test your code with this in classes, because you have simple projects in classes. And sometimes you have limiting cases, or you can simplify your code to have an exact solution. More often than not, it doesn't exist. And so there is a way to do that, and that's called the method of manufactured solutions. It's called the method of manufactured physics, or the method of manufactured universes, but I think those circles are stupid, because I think those names are ridiculous. And so I go with the method of manufactured solutions. And what we do here is say we have a solution of PDEs, partial differential equations, right? And we don't know what the answer is. In order to use the method of manufactured solutions, we simply guess our own solution. There is going to be a little math, but it's mostly to illustrate some software. So hence Gauss's equation, right? Or heat equation, right? And in 2 dimensions, we can represent it this way. And let's get a manufacturer solution. I'm going to just suppose putting these constants in there, give me the solution. And when I solve the problem, there's no surprise that the residual is non-zero. If I could just open my eyes real big and guess the solution to those system of equations, I would be doing something else with my life. So there is a non-zero solution. That's a residual. However, if we take that residual and add it to the right-hand side as the source term, we can solve the problem. And then we can use this manufactured solution to verify our numerical scheme. Right? Have you ever heard of a code being like order n squared or order n log n? Right? P versus NP, that kind of stuff. Right? That's the rate of convergence of the numerical method. That is, how should the error decrease as I change the number of elements in the solution? So we can use these manufactured solutions to test the numerical method. Now, when I do this for my code, does this tell me that the physics is right? No. Does it tell me that the numerical method implementation is correct? In fact, you can use this to find bugs. So again, I realize most people in the room won't be doing this, but I wanted you to give a feel for the kind of stuff you can do to find bugs in physics software. You know, most people, especially if you watch a lot of CSI or Mr. Robot or anything like that, to find bugs, you open up something in a text editor, open your eyes real big, and stare at it. Oh, there's the error, right? In the real world, that doesn't work very well. Our codes are long, they're complex. So here's an example on a real problem. This was finding a bug in Finesse. Finesse is a hypersonic flow solver, fully implicit Navier-Stokes. It also has some other physics in it for solving problems related to atmospheric vehicle entry that we wrote for NASA. And we had something called the Spilart-Omaris turbulence model. And when we first got the code and we generated the asymptotic convergence analysis, that is, we looked at as a function of the number of elements. These are always log-log plots, right? So 10, 100, 1,000, 10,000 elements. The error should decay. And we know that because of the numerical method we're using. At first, looks like, and if you were to just do this in the eyeball norm, chi by eye, linearly squint, right? It looks almost second order for the first couple of points, right? But then it levels off. It turns out, order of operations, right? In this representation, it's easy to see the bug. In the actual C++ operator overloaded, heavily templated metaprogramming code, it was hard to see the error. And in fact, there actually turned out to be even a second error on top of that, having to do with the shock capture. We use something called SUP-G, stream upwise Petrov Galerkin. That is, you have, when you're going from hypersonic to supersonic, you have these large changes in pressure, and they create almost like a numerical instability, kind of like a singularity, but not quite. And so we have to have some shock capturing algorithms to stabilize the numerics. And we were able to find another bug due to this type of work. Okay. So what have we learned? You can generate a manufactured solution for any system that does not have exact solutions. MMS is very popular, although it's not done very often. Why? It's hard to generate the solution, or it's hard to generate the residual. And providing high accuracy code, or providing code to help verify your code, is very hard. I'm going to take a simple example. This is from the literature, from a paper by Roy et al., where they have a 10-parameter trigonometric solution of this form. We then solve it with a symbolic package, Maple, Mathematica, SymPy, one of those. And that'll give us the residual term. This is a relatively simple problem. We've had manufactured solutions that gave us 31 pages of terms. But we then get this as our C code. And we can use this to verify our code. In fact, fun story, we were working with Maple. And when you exported the residual term, it gave you a copy-paste buffer, but it also gave you a way to export it into MathML. Have anyone heard of MathML? It's math markup language. It's like a JavaScript or Java kind of implementation of markup for math. It's like LaTeX for Java means, right? And MathML was implemented in Maple to stop copy-paste bugs. Because as you can see, a copy-paste bug in this would be hard to find. So we used MathML, and we exported the solution to our code. And we spent 2 months trying to find our bug in our code. And we could not find a bug in our code. on a whim, celebrate a PhD of one of my students, came back to the office and just used the copy-paste buffer. My code converged perfectly. There was a bug in Maple's MathML export and not in my code. And I was using Maple to find a bug in my code. We contacted Maple. We told them they had a bug. They said, lol, no. I filed a support ticket. A couple months later, they emailed us back and said they just pushed out a patch. So that made me feel good. Depressed, because we spent so much time on it, but good. All right. So in order to solve the problem of dealing with high accuracy manufactured solutions, we did what any good people do. We developed software to do it. So I'm not going to go into too much detail into MASA. MASA stands for Manufactured Analytical Solutions Abstraction Library. That was a stretch, but before I came to UT Dallas, I worked in the PECO Center, and all our software had Mexican themes. We had queso, we had chips. In fact, chips was a hypersonic code, and queso was a code for doing uncertainty quantification. So when we did uncertainty quantification on hypersonic codes, we had chips with queso. MASA is our library, which is on GitHub, and its goal is to provide a standard interface for MMS usage and preserve extreme fidelity, be portable, traceable, and extensible. Our original goal was to reproduce an absolute error within 10 to the negative 15. And we wanted to support all compilers for some subset of all. GNU, Intel, and PGI, because we were working on a lot of DOE systems at the time. And just compiling with O0 was not sufficient to preserve even relative 10 to the negative 15 error. For the Intel compilers, you have to turn on an extra flag called FP model precise. To me, this should be on by default. The GNU one is no unsafe math optimizations. That's really disconcerting. Is that on O0, we think of O0 to mean no optimizations. We would like to think O0 means no optimizations, but it doesn't. Right? That's what I'm pointing out. How many else knew that? Okay, so now everyone knows that. No unsafe math optimizations. If you're curious what they were doing, they were on that they're truncating transcendental series, right? So all transcendental functions, sine, cosine, e, etc., they're represented as a series expansion, and the series expansion has a number of polynomial terms equal to the precision required to preserve it. They randomly truncate in order to make it faster. The PGI one, of course, is the very logical -k IEEE MN of P of prox. Being very accurate is hard. Remember yesterday when everyone was making fun of me for all the versions of Python I had installed? This is why. We provide SWIG interfaces for MASA, so you can do MMS in Python. It's actually really cool. You can import MASA from Python at the command line and query manufactured solutions for input variables. In order to preserve 10 to the negative 15 of precision, we test every version of Python, every dot release. And it changes. Every couple of dot releases, the residuals we get change. All right, now the rest of the MASA stuff, I wanted to give you as an example of what a good software ecosystem looks like. So if you go to our Git, yes?
When you're testing all of those Python modules, is that all automated?
No. So we write the tests, and we built a system. So just like there's AutoConf that makes makefiles, right? We built a system that builds software and builds module files. So, have you ever used like LMOD or environmental variables? Yeah. So all those dependencies and all those hierarchical modules, we have a system of scripts that builds that for every particular version that we support. And then it's run automatically. So I have a cluster of 640 cores that do nothing but run tests constantly. So anytime something's checked into a GitHub or SVN repo for one of my projects, regression tests are automatically run between all linear combinations of compilers and languages and MPI stacks. In fact, that's one thing I'll talk about. One of the things you can do as a supporter of cyber infrastructure is provide a CI server, a continuous integration server for your PIs to use. And caveat time, I can talk about some options. All right, so these next couple of slides, I just want to give you an example of what I think a healthy open source science project should look like. So if you go to our GitHub page, you'll see all this stuff. You'll see our software environment. You'll see our testing, our line coverage. We do code and we do function and line coverage. We're at about 98% plus of line coverage, which is actually amazing. Most line coverages are around 80% as their standard. We have automatic documentation produced by Doxygen for marking up the API, as well as for writing out the mathematics of the actual problems in there. We have a bunch of manufactured solutions we've already generated, mostly on the flow side. You can import new solutions. This is very powerful. If you want to write a manufactured solution, but you want to build on top of all the infrastructure we have for APIs across languages, as well as numerical accuracy support, you can use our infrastructure and pull in your own C, C++, or Fortran manufactured solutions. But this is hard. Manufacturing all these solutions, especially on complex problems, is very difficult and time-consuming. So what do? We replace that person with software. So inner automatic differentiation. One of the things we're working on is our cleverly named package Metaphysical, which does compile time header-only C++ automatic differentiation. But the idea of where we're going, caveat funding, it's one of the proposals I'm working on right now. The idea is you write up your PDEs or your ODEs or whatever in LaTeX. Then that gets parsed by Masa, uses AD to automatically generate the manufactured solution, and then imports that solution, which you can then use to test your code. Coming to a GitHub server near you, 2020, 2021, something like that. I'm currently trying to get some DOE funding to do this. They're very interested in it. All right, Masa. So this is the kind of stuff you should look for when you're looking at software. It has a version number. That's good. It's not just mycode.tar.gz, right? There's two things when I look at a new code that make me disqualified immediately. One is if it doesn't have a name or a version number. Two, if I download that code, right? For me, that would be right-click the link, open up a terminal, wget the file. What's the worst thing it can do?
No directory structure.
Crap on your working directory. If the writer of the software does not have respect for your current working directory, you should not have respect for that software developer. Right? So no directory structure. If on the website and a citation, that means the person wants you to
Cite it.
well, first,
Read the paper.
use their software,
Oh, yeah.
and then cite it. Much to my dismay, I get many, many more citations from some little one-off code I write to do something than I do from any of the science I've ever done. And it's depressing, and it's caused me to change career trajectory over the course of my life. But citing software is a good way to build your reference count, your citation count. All right. So how do you find these software packages? What do I have, about 2.5 more hours?
Almost.
So I'll go to like 245 plus questions or something like that.
That sounds about right. Yeah.
250. Okay. All right. So the first thing you want to do is define what you want from the package, or in the case of you supporting a PI, ask them what they want from the package. It's a much better conversation to say for the faculty member to say, I want this package in this version. It's a much better conversation to say, I want this capability. We want to be able to define what a package aims to provide. So how do you find these packages? Talk to other users in your field. If you find a package you want to use, talk to the developer. If you go to a web page and there's just a tarball on it, they probably are publishing it because their NSF program manager said they had to. But if you go to a page, there's a download, there's version control, there's documentation, there's a chat room, there's Twitter, there's Instagram, there's Facebook, there's an email link, there's a phone number. He's dying or she's dying to hear from you. They've spent all their blood, sweat, and tears writing this software, and they want nothing more than to talk to someone about it. Right? So if they provide their contact information, reach out to them, talk to them. Ask them what they consider to be stable versus unstable in their code. Ask them, is there a way to contribute? Ask them if there's a way to cite. Look at the mailing list, see if there's any traffic. Those are all good indications. All right, when you download some things to pay attention to, these are the things that make me disqualify, or in the case of PI support, yes.
Sorry, from TD Land, and this rolls back a few minutes. Do you or anyone keep a catalog of the Python changes?
Not as much as I should. Now, I have, so as part of our testing, we write a single regression test ever run to an HDF5 database. So I have all the diffs. Have I looked at them recently? You know, a lot of you have heard that I've transitioned to UT Dallas over the last 3 months. Before this, I wrote this in a past life where we had a research group of about 20 people, all working on software engineering type projects, and then all our funding got cut within a couple of months. So these are projects that are currently still running but not funded, and then I'm currently looking for funding for. However, if someone wants to go through back all the the HDF5 solutions and look at the changes, I'm happy to provide the data. All right. So these next couple of bullet points are the things that really allow me to identify bad code quickly. Variable names. Are the variables named var1, var2, xxx, xxy, xyz? If they have that kind of naming, that is a big red flag. If all their code and their build systems and their include files and their module files are hard-coded to /lib/libftw.a or whatever, if they're hard-coded, that throws a flag up in my mind. I want to see that they've thought about and have run it on multiple systems. Formatting of the source code. Now, I'm not going to go into the religious war that has tabbed these spaces. Of course, the people who use tabs are obviously wrong. I'm just kidding. I just come from a Fortran world, so I'm used to it. And I don't care if it's 2 versus 4 spaces for a tab. All I care is that the developer had a preference and that they're consistent. That means they care about their source code. If the default build system explicitly turns off all warnings and errors because they don't want to read them, red flag. I want to see warnings on by default in the build systems. If /configure and make work, but make check is not defined as a target, red flag. right? If there's no test suite, if there's no way for me to ascertain whether this code is doing what I think it's going to do, red flag, maybe a yellow flag, caution. I wouldn't necessarily exclude it, but I would bring it up in a discussion with the developer. All right, other things to note.
Chris?
Yeah.
From TV land,
Huh?
these criteria may exclude a lot of bioinformatics code, especially the no test suite. And by the way, I was thinking the same thing.
No,
So what if you're in a sub-discipline where there's one code? And there are a lot of them. Most sub-disciplines, that's true.
Aspire your community to do better, but accept the reality of your situation. Right? Now, I did preface the talk by saying what area I was focusing on, but that's a scapegoat, right? There are lots of one package to rule them all Tolkien type of situations, right? And you have to use a package because everyone else uses a package. Now, if you want to develop something, you can, and you can do better, and you can gain lots of support by doing better. Or you can accept your fate, adopt the package, ask if you can contribute, and improve it.
What if you are not a code developer at all?
Then you can get your, are you a student researcher, or are you a researcher?
Faculty member.
If you're a faculty member, get funding. Make a partner in the CS department or your computational science department. Work on interdisciplinary proposals. NSF, NIH, SI2 proposals would love things like this. They would love to take community codes and raise the software standard. Be better than your peers. Desire for more. Reach out and do better. If you're a researcher or a staff member who's supporting a faculty member, then all you can do is ask for acceptance metrics. That is, you have a faculty member that says, I need this code. It needs to be this version, and I need it on your latest, greatest cluster. You get it, you download it, you compile it, you say there's no test suite. What I ask for then is I say, give me an input file and give me an expected output. And that's all you can do. Does that address all possible iterations of the question?
Oh no, it gets much worse from there, but that's probably far enough.
What time the beer come?
Yeah, I barely scratched the surface of how
So-
bad it can be.
Actually, I think this topic is fascinating. And I think in the future we should maybe organize something around it. I have lots of thoughts about how to deal with it. I have opinions on everything. One of the reasons I'm divorced. But one in a minute. But something like this is of interest to me. And this is actually something I'd like to get involved in. You know, in my previous life, I spent my entire life writing proposals to do science and supporting a big research staff. Now I'm 12 months hard money. And part of my job, as mandated by my boss, is to reach out with other universities, educate, travel around and do this kind of talking, right? As well as try to collaborate and come up with proposals to do better. And software excellence is one of my passions, and I love it. So let's make a positive change in the world. All right. Other things to consider. Finding a bug in software does not rule it out. Every software has bugs. All your commercial software has bugs. In fact, finding a bug is an opportunity to spur collaboration. Many times I have found bug in insert popular open source software in here. You know what I do? I reach out, ask if they accept patches, fix the bug, submit a patch. Now the community has been bettered for it, and now the developer kind of owes me. Now the developer will implement a feature for me in the future. I fix his code, he scratches my back, right? That kind of stuff. Always pay attention to licensing. Licensing will bite you more often than not if you don't pay attention to it. It doesn't mean you preclude commercial codes. It means you recognize the use cases and the limitations up front. Another good rule of thumb is if TAC or insert HPC system here has a module for it, it's worth evaluating. If TAC or NCSA or SDSC or PIT or any of the other supercomputing centers has pushed out a software support for it, that means at least someone has looked at it and built it and has some confidence in its capability. Commercial software doesn't always mean high quality. And be polite to the developers. I'm on many software support email lists, and it's amazing how many first-time contacts I get who complains about their fault or our fault, but we're not likely to help them if you're a jerk, if they come off as a jerk. All right. Any questions about generally evaluating software? TV land? Okay. Sometimes you have to bite the bullet. Sometimes you have to write software. That doesn't mean you have to write all the software, but sometimes over the course of working on a PhD or working, you're going to have to write some software. Always consider the language and the applicability. So many times I've seen one-off MATLAB or one-off Python or one-off Perl scripts, right, that have become the major workhorse of a large multi-million-dollar research group, right? MATLAB has its place. Its place is not always on an HPC system. It can be. It depends upon the workload. If you're using specialized toolboxes that have optimized backends in C, C++, or GPU. If you have the ability to afford the very expensive parallel stuff. But it's not always the best solution. You need to think about the system you're going to run on. A lot of times I've seen these special software developed for, like Henry, you were talking earlier about Blue Gene systems, right? Blue Gene workloads look a lot more like K&L than they look like traditional fat CPUs. A lot of low power, low core processors that have a very good interconnect, right? If you write your software to do amazingly well on this latest, greatest special FPGA, and all of a sudden Intel decides next year, oh no, we really did mean to write KNS, right? Or they just say screw it and buy NVIDIA. And so it's Intel, NVIDIA versus AMD, and AMD loses twice. Or at least has a hard time competing fairly. So consider where you're going to run it. Open source and free, and when I say free, I mean both Libre and gratis. I mean both no cost as well as have the source, versus performant. So when I'm developing some software, compiled code, C, C++, Fortran, I always support two stacks. I always support the open source stack that's always going to be free, and I always support the latest, greatest, fastest, commercial, all the bells and whistles. So in my world, that tends to mean C++ or Fortran. It always means BLAS, basic linear algebra subroutines. And it always means MPI. So on the open source side, I'm GNU compilers. I'm Open BLAS for the BLAS. And I'm typically MVAPITch if I'm on InfiniBand, or MPitch if I'm on standard interconnects. Don't use netlib BLAS. Don't use Atlas BLAS. They're slow, right? Open BLAS has some of the advantages of these microcode optimized kernels, but it's free. And then on the performance side, especially if I'm working with Fortran, I work with the Intel compilers. The Intel compilers, especially their Fortran compilers, are fast. It doesn't mean they're correct. It just means they're fast, right? Fortran compilers have been around forever, right? Fortran compilers predate Unix by almost, what, 20 years? You were talking about Alpha and DEC earlier, right? That Fortran compilers, which were written for the DEC, bought up by Compaq, actually became the Intel compilers. Those original DEC Alpha floating point Fortran Beast compilers are now Intel's compilers. Why does Intel write a compiler? Do they write a compiler to make a couple $100 on a software license? No. Why does Intel write a compiler?
Make their hardware look good.
To sell processors. What makes their processors want to be bought? They're fast, right? GNU strives to compile fast code, compile fast, then compile correct, then run fast. Intel strives for running really, really frickin' fast. Takes a long time to compile, and is probably wrong. But usually within a sufficient tolerance. Yes?
From TV Land, how about adding a reusable spec file or equivalent for non-packaging systems to make, for non-RPM systems, to make homogeneous builds using different compilers?
Short answer or long answer?
That sort of vaguely sounds like they're referring to something like Easy Build or SPAC.
SPAC is where I was going. The short answer was yes. The long answer would be something like SPAC. SPAC is really cool. SPAC takes concepts from the, what is it called? Anyway, with SPAC, you can specify a package you want to compile as well as within a spec file, get another markup language. All the various linear combinations of compilers, versions, and MPI stacks you want to build, and then you run SPAC, and it generates all the linear combinations of it for you automatically. So if you want to build lots of software on Linux, I recommend using OpenHPC and SPAC. Now, disclaimer, I'm on the OpenHPC Technical Steering Committee, so I have a vested interest in people using OpenHPC, but in my defense, it's really, really cool. So OpenHPC will set up the GNU compilers, all your MPI stacks, module files for the Intel compilers, all your Python stacks, all your various combinations of support libraries, your netCDFs, your HDFs, your parallel HDFs, your FFTs, and then SPAC will build your applications using all those various linear combinations of support libraries. So once you then update and get a new compiler version or a new MPI version or a new MPI stack, you then update the SPAC build and it fills in all your dependencies. In fact, that might be a good tutorial to do one of these days. All right. So we've decided we're going to write some code. We need a place to work, which means we're ready to start using version control. When you decide to write code, the first thing you do is create a place for it to live. If you're working in SVN, you need some structure which looks like this, right? Here's our trunk, branches, and tags. Here's our typical directory structure. In Git, it would just be this at the top level, and we'd use branches within Git branches for dealing with it. Once you're ready to start writing code, the first thing you do is take a text editor and you open a LaTeX file. When you're ready to writing code, you're not actually ready to writing code. You're ready to start writing documentation. Starting a coding project means starting a document to describe what you're going to write. It doesn't mean opening a source file and start typing random and trying to implement something. Before you implement everything, you should be able to write down precisely what you plan to implement. Otherwise, you know what? You're not ready to implement. But Chris, this takes a long time. No, it doesn't. It saves you time. This document you write here is what you're going to use when you write the paper. It's what you're going to use if you're writing a dissertation. It's what you're going to use so that you can actually sleep well at night. And if you don't do it, it'll disturb me and I won't sleep well at night. All right. What goes in your model documentation? Everything necessary to implement your application. Your governing equations, your boundary conditions, your discretization approach, your solution technique, how you plan to ascertain you're correct or not, your verification plan. This is a model document, not a code document, not a developer's guide, not a user's guide. And I have some examples of these. Maybe I'll send it around to the mailing list in the future. All right, so here's an example of a model document. It doesn't mean it has to be long. So here's one we were doing on a log layer validation, like a turbulent boundary layer problem. The model for the overlap layer mean velocity models, the data we're using as part of the Bayesian inference problem, the Bayesian calibration problem, and our verification plan. So, 10 pages or so. All right, now that you have a model document, you know what you're going to implement. The next thing you do is open a web browser, not open a source file. It's to determine what software we can outsource. Just because you're writing your own software doesn't mean you write all the software. Know what capabilities we desire, know where the science is, and know what we can outsource. Never write your own input parser. It's important, so I'll say it again. Never write your own input parser. There's the old CS joke that says, how many PhDs does it take to write an input parser? I didn't say it was a funny joke. I said it was a CS joke. But it's meant to underscore how hard writing an input parser is. So what I recommend doing is use the input parser I wrote. It's a little hypocritical. But it's not, our group wrote one that's built on top of Gitpot. And Gitpot's an excellent input parser. So that's one I would suggest. If you're working in C++ and you're already working in the Boost ecosystem, use Boost programming options, right? Use an input parser that's been verified. That right there will save you days, if not longer, of your life. Never write your own solver. Unless you're doing research in applied mathematics, and doing researchers and solvers, don't write your own solver. There are people who spend their entire lives writing assembly-based microcode for optimizing dense matrix-matrix multiplies. Your stupid numerical recipes LU decomposition is not going to be faster. Use solvers. Use Petsy. Use Trilinos. Use GSL. Use Eigen. Don't write your own solver. Unless you're doing research in finite elements or finite volume. Use someone else's library. Use OpenFOAM. Use Deal2. Use libmesh. Don't write your own random number generator. Don't write your own spline routine. Don't write your own linear fit, right? Your own linear least squares. Use GSL. Anything you can outsource to good, high-quality software, do. Anything you can outsource to programs that meet the requirements I covered earlier. Anything you can outsource to programs that are installed as part of ROCs or OpenHPC or in HPC centers. That's not your direct area of research. Outsource. Use their building blocks. Stand on the shoulder of software giants so you can see further and perhaps graduate. All right, so for this particular project, I was interested in uncertainty quantification. So I didn't need to write an input parser. I didn't need to write my own numerical algorithms. I didn't need to write statistical code. I only had to write the part of the code I needed to work on. You decided you want to write a code, so you wrote some documentation. You decided you want to write a code, so you opened a web browser and selected some software. You decided you want to write a code, so now you're ready to build a build system. You're not ready to write code yet. Right? It could be a simple build system. It could be a bash script that does your linking. I would recommend starting with a simple makefile. You're ready to start writing code. So now you're ready to start writing tests, right? You're finally ready to start writing code. So as you're writing code, you write tests along with it. And I'm not going to talk too much about unit testing and actually doing it. However, as a facilitator, here's some software you can install to encourage it. These are tools used as part of the trade. In C, C++, a lot of people like CU test. I prefer CPP unit, mostly because there's a suite of unit testing frameworks that are splat unit. There's CPP unit, there's F unit, there's X unit for MATLAB, there's R unit for R, so it makes it consistent. If you're working in C, C++ only and already in the Boost ecosystem, use Boost Test. MATLAB, believe it or not, has unit testing frameworks. Python has one called Nose. It's actually really cool and easy to use. Use unit testing frameworks. Make your job easier. Testing is very important. Testing is the only way you make progress through life. Reuse as much code as possible, right? Choose your MPI stacks, choose your BLAs, choose your solvers, choose your finite elements. Don't reinvent the wheel. Time spent rewriting something old is time that could have spent developing something new. All right. Someone asked earlier about, one code in a field, right? And that was in bioinformatics, I believe, Henry, right?
Well, it's by no means constrained.
But that was what the question was
That was
about.
when the question came up, yeah.
Yeah. So I have experience. It's very specialized that had one code. So a couple of years ago, well, 10, 12 years ago, we started a research center doing work in hypersonic flow for atmospheric reentry vehicles, basically being funded to work on the NASA problem. And they had a code called Deepler, which they believe to be truth. And they've used it in several successful missions, right? It's what they used to send things to Mars, and it worked when they got the units correct. And so it's what they accept as truth. However, we were interested in working on that problem, but also doing work in advanced numerical analysis. So we needed some instrumentation in the code that wasn't available. So we had to write our own hypersonic flow code. Except whenever we wanted to show that it was correct, all the people in the field, the domain experts say, I don't care about your verification, your unit tests and everything. How does it compare to our code? And this is called code-to-code verification. And my main point of this slide is to try to resist the temptation of doing it. Because the exercise is often useless. So here we have two codes. One uses finite elements, one uses finite difference. The other one, they have different models, they have different subphysics, they have different discretizations. On a particular problem, at a certain scale, they're going to be different. Here we have a picture that we showed, and if you zoom out far enough, they're on top of each other. And this looks great. But if you zoom in and start looking at the actual differences, they're differences. So the two codes are different. What does that tell you? The two codes are different. Right? So a lot of people in a lot of communities are vested in code-to-code comparisons. I caution you from doing that. There's a lot of things you can do when developing a code to allow easier construction of answers. One really cool technique is in every term, put a simple multiplicative factor. And either set it to 0 or 1. And by default, it's 1. But You can selectively turn off subphysics and generate simpler model prompts. Or you get a bug and you can we've done this before, write a linear combination or a combinatorial number of input files that turn off and on all possible combinations of physics and do that asymptotic convergence analysis. And you can see for what combination of terms does this work and what combination of terms does this error approach. So even as something as simple as putting a multiplicative factor on a lot of your source terms makes generation of tests easier. Symmetry is often overlooked. Sometimes all you know about a code is symmetry in should give you symmetry out. And a lot of times that can be used to identify bugs. This is a particularly powerful technique. As a lot of researchers are moving into more advanced numerical fields, they start using off-diagonal terms, they start using Jacobians, they start doing coupled multiphysics, or implicit solves, or error estimations, or grid refinement. Any of these terms means higher order information. Higher order information means Jacobians and or Hessians, or third derivatives if you're feeling fancy, right? And any analytical Jacobian or Hessian, you can verify by finite difference. So a lot of times you can find errors in Jacobians, which are subtle, especially if you're doing an implicit solve as your numerical technique. Things with error in the Jacobians will converge to the correct answer eventually, just a different order of accuracy. So this is a good way of finding errors in Jacobians. Verification never ends. New feature, new optimization, new combination of physics, new data, new requirements. That means new verification. That means rerunning your verification tests. That means, as a support staff, providing a framework for your researchers to automate testing. Now, if your researchers are using GitHub CI server, right? Has anyone used it before? It's called Travis CI. It has a free CI, but it only runs on Ubuntu mostly, and it doesn't really have all the combinations. So providing a CI server locally, especially that has the same software stack as your HPC system, is a very important tool you can provide to help catalyze software excellence. The two projects that I'm going to recommend you look at are BuildBot and Jenkins. BuildBot is Python. It's really easy to integrate with Apache. It doesn't look very pretty, but it's really easy to set up. Jenkins is a full-fledged JVM. You can deploy it using any of your favorite Java container deployment programs and just have it implemented on your virtual server, and you have a Jenkins VM. I use both. They're very good. All right. Conclusions. Generally accepted recommendations. Show other people your code early and often. Reuse good software and evaluate multiple options. Use platform-independent files whenever possible. This is less of an issue these days because mostly little Indian systems have one. You guys know the difference between big Indian and little Indian? You ever heard those terms?
But I'm willing to bet there's a significant
Okay.
of people who don't.
So all the systems we work on these days, x86 or x86-64 systems, are little Indian. In the 32-bit or 64-bit representation, it means you write the least significant bit first. It's from the little end to the big end, right? Big Indian means you write the most significant bit first to the least significant bit first. So if you have a big Indian file on a little Indian system, you'll read every bit in the wrong order, but your program doesn't know it. So you want to use a platform-independent file format. If you want low level, we used to use something called XDR, FXDR for Fortran. These days, we tend to use platform-independent files. Unless you have a reason otherwise, I would recommend using something like HDF, right? Hierarchical data format, HDF5, or NetCDF, or some other type of I/O library that handles this. When you're designing systems, always consider performance versus portability. Always consider Libre and Gratis versus I have all the money in the world. I always prefer open source solutions. Commercial products scare me. And when something doesn't work, I can look at the source code and figure out why. Don't write your own input parser. Don't write your own solver. Don't write anything unless there's something out there that doesn't meet your needs. Unix. Learn as much Unix as you can tolerate. I think Unix is an amazing thing, and over the course of my career, I've seen a huge correlation between success and the amount of Unix that someone knows. Now, is it correlation or causation? Yes. Doesn't matter. Doesn't matter to me because I see it. Learn as much Unix as you can tolerate. Highly opinionated recommendations. Learn a console-based text editor. Learn how to spell editor. Then learn a console-based text editor. Right? The amount of time that I see people spending downloading files, opening in Sublime, editing the files, quitting it, connecting to VPN, copying it to the HPC system, submitting your job to Slurm. Oh no, there's a Q submission error, there's a syntax error. Download the file. It's ridiculous. My main philosophy in life, in terms of productivity, is the tools I use remotely are the same tools I use locally. That is, I use VI, I use Bash, right? I use LaTeX. That's all I do. That's everything. Learn LaTeX. Yes, it's better. Learn LaTeX, especially if you're writing equations. Learn LaTeX. Especially because it's a text-based format. What goes well with a text-based format?
Text-based editor.
Text-based editor. And?
Sorry, I'm going to answer your question. I have a separate question.
And version control.
So what if you're in a discipline where nobody else knows LaTeX and it's expected that you share your document files with others? And I don't mean the readable version. I mean the editable version.
I weep. And it happens.
I would argue that it is the most common. That I only know 2 disciplines where LaTeX is common and considered normal, CS and physics.
And chemistry and engineering. At least, well, let me put it this way. I've chosen to collaborate with people that self-select, that I end up writing more in LaTeX than Word.
So I would argue that if you're going to be multidisciplinary, as many of us are,
right,
it would be valuable to know LaTeX. At the same time, within a given discipline, it may be literally impossible to use it.
I'm not saying at the exclusion of reluctantly using Word. Sometimes you have to. I have a Windows machine because I have to connect to an Exchange server these days. And I have to open Excel files and Word files. On that note, Henry mentioned editable file formats. When you're mailing on an official document, don't send out an editable file format. Send out PDFs. Don't send out announcements in doc files or PowerPoints or Excel spreadsheets, because you never know who changes what, and your name's still on it. Right? It's in the metadata. Only send out PDFs. Don't send out resumes and doc files. I don't read any resumes that get sent to me in Word. Learn a scripting language. In my day, that was Perl. These days, I would recommend Python. Right? Just because of the white space requirements, it's easier to pick up someone else's Python and work with it than Perl. And Perl really is a community that prides itself on obfuscation. It's like, haha, you can't read my Perl if you just lol and just deleted your home directory, right? I think that's really funny. I don't think it's good for reproducibility in science. So I recommend learning Python. Learn a Unix shell. Don't just know how to get around in Bash. On a typical Unix system, how many commands are there in your path? Just guess.
2,000.
2,000 to 4,000. How many commands do people actually use?
2.
5, 10, 20, something like that. One of the reasons Unix is so powerful is the way you interact with it is a programming language. Bash is totally complete. Bash is a programming language. So if there's a feature that's not implemented that you want to do, you write it interactively. You just write the program. Knowing a Unix shell will increase your productivity by several multiplicative factors. Realize that Unix is self-documented. Right? We always want to go to Google, and then we always find, the answer posted as a link on Stack Exchange, and then you follow that link to the GeoCities page, which is no longer available. Man minus K, right? Searches all man pages. Remember that man's your friend. Now, as sysadmins and supporter of HPC software, if you understand these 5 things, you will be a superstar compared to your colleagues. Actually understand the compiling and link cycle. Understand the difference between static and dynamic libraries. This right here is probably 1/3 of your support tickets on an HPC system. Understand processor optimization, and how the advanced instruction sets work with compilers. Our processors are faster these days because of optimization, not because of raw floating point and 1 gigahertz. Understand the storage hierarchy, local versus network disk versus memory versus cache. And understand LD library path. Yes, sir.
A couple of comments.
Okay.
Several comments.
All right.
From TV Land. So a little bit of sed, grep, and awk helps a lot for particularly system administration use. And I'll add in my own comment, I'm not a system administrator, but I'm addicted to those 3.
Yeah, I would add, excuse me, I would add learning regular expressions.
Yeah, I would tend to agree. So how many of you are familiar with sed? Okay, grep, how many familiar with grep? And awk. Okay, so.
I would add fun.
Okay, so how many of you are familiar with find? Okay, so sed converts some characters into other characters in a pile of text.
Sed stands for stream memory, right? It edits files in a stream of data.
Grep searches for patterns within a pile of text, typically a file or a collection of files. Awk is a little baby programming language that is somewhat similar to a very, very stripped down version of C, but is also different in a number of ways.
I would say if sed and Perl had a baby.
Yeah, probably. And find just finds files in your directory structure.
Find is weird because the syntax doesn't come from the Unix standard. It comes from a different history.
Right.
And so it has a weird syntax, but it's extremely powerful.
Wait, there's more.
Okay.
Another person says, even just cat, pipe to cut, pipe to sort, pipe to join can be very helpful.
Yeah.
Right? Another person says, productivity goes up on shell if you reuse your knowledge of either VI or Emacs or Vim and take advantage of set-o VI or set-o Emacs. And another person says, I use awk for parsing. And another person says, the Silver Searcher, IEAG, OAG, will do find plus grep easier and faster.
That's true. It's true. And I would add to that, if you're working with high-performance file systems, like Lustre, that you learn to use things like LFS find. Also, LFS set stripe, if you want some actual performance from your Lustre file system. I mean, we could have a week-long discussion on just how to be better at Unix. In fact, when I teach my introduction to computational science, I have a 2-week lecture on Unix. So. All right. More things to understand. Actually learn how to use the compiler. How many people read compiler man pages for fun? They're an amazing resource. They are long. In fact, one of my homework assignments for my my tools and techniques of computational science class, is I make them find a typo in both the GNU and the Intel man pages. Some versions, they don't have one. Learn about the hardware, what we refer to as speeds and feeds. Learn roughly bandwidth and latency for all parts of the machine. You don't have to know tons of architecture, just enough to get by. Learn a little bit about debugging and profiling. Again, these are classes that, these are lectures that I teach for an entire or multiple classes. We could teach semesters on debugging and profiling, but just knowing a little bit about G2B, Valgrind, MPIP, Tau, PAPI, any of these tools are extremely powerful and can get you a long way. If you're a software developer, always have a restart capacity. A restart capability. That means be able to stop your job at a particular point in time and checkpoint it, write to disk, resubmit a job, and resume it. All right, my soapbox. Use text-based formats and version control whenever possible. I version control everything. All my dot files are managed on GitHub. I keep them all synchronized between every system. All my input files, my Slurm files, my output files, if they're text-based, are on version control. This talk is on version control. I put this talk together between combining multiple talks. All my posters, all my papers, my dissertation. Everything is in version control. Everything is text-based. All my plots are text-based. That is, I don't save the output. I save the raw data, and I save the script to generate the GNU plot or the matplotlib. All those are version controlled. Everything in my life is version controlled. Keep as much of your life as possible out of email. Email is the death of productivity. Yes?
So what do you do when within a particular standard that you're using under version control, the version of whatever it is ages out? Like my dissertation was written in LaTeX, and it cannot be built now.
Okay.
Happily, I saved the PDF, but I can't build it now because many of the commands are no longer in LaTeX.
Well, I'm not as old as you, apparently.
I'm going to guess we're about the same age.
I think you're older than I am. I don't know. I'm 43.
Okay, I'm a bit older.
Okay. By about 6.5, 7 years.
9.
9? We were going by the Price is Right rules, so I was close.
Yeah.
Okay. I actually haven't encountered that problem, and I would have to imagine it would be available somewhere. And you didn't save the style files or anything?
Sure, but
okay.
some
Send me
of
the
them were.
send me the tech file. I bet you I can build it. Check your version control repo.
The difficulty is that much of it was built on a system that had a set of defaults.
Okay.
I didn't know in the mid-90s not to assume the defaults would always be there.
Fair enough. Fair enough. I haven't encountered that problem, but now that you mentioned it, I'm not going to sleep tonight, and I'm going to think about how to avoid it in the future. All right. Last requirements. Check out OpenHPC. Even if you're doing nothing more than installing workstations for your research faculty or Linux laptops, you can use OpenHPC. That means you can download their software repositories and have multiple compiler stacks, LMOD, R, all your BLAS libraries, all your supporting software that comes on an HPC center on your laptop or on your workstation. And then it'll be just like tax systems or just like your cluster. Again, I'm affiliated with OpenHPC, but I think it's pretty cool. And finally, as you guys know, be nice to sysadmins. No one ever comes up to an Exchange server and say, my email worked all day, great job, right? So I always try to tell everyone to be nice to sysadmins. It'll make their day. And with that, I go to my end slide. So XPCD a couple of days ago, guidelines for airplane safety. We got an idea what we're doing. Elevator safety, we got an idea what we're doing. asking software engineers about computerized voting. That's terrifying. Wait, really? Don't trust voting software and don't listen to anyone who tells you it's safe. I don't quite know how to put this, but our entire field is bad at what we do, and if you rely on us, everyone will die. Blockchain, no, that doesn't work. Yesterday, 243% voter turnout in parts of Georgia. And at the same day, a couple days ago, John McAfee challenged anyone to hack his Bitcoin wallet. So it all kind of comes full circle. Software is not something you have to suck at, but it's something that most people do because they're not willing to put in the time, because funding agencies typically fund science and not software. However, as with anything that has a startup penalty, there's a crossing point. There's a point at which this is your progress over time. You start coding immediately, you make progress with science, right? If you do things properly, your productivity short-term will be slow, will be less. But the turning point, the inflection point, the point at which your productivity passes because you do things properly, is not as far along in the time domain as you think. Doing this always saves you time in the long run. But most people are focused on doing things right now and not right. And with that, I'll take any final questions. Or not. Well then, thanks. Any more questions from TV land?
A question.
Oh, yes.
So do you plan to collect 100,000?
Oh. I don't need it. I bought 100 Bitcoin at $1 each many years ago. And I can retire whenever I want. So I'd rather spend my time helping people do science. But I got lucky in the crypto market. So it bought my house and it paid for both my kids to go to college. They haven't yet. So, and allows me to keep working in academia. Other questions? All right, well, I'm about to head out. I gotta go back to Dallas and put out some fires. But Henry, I want to thank you for inviting me.
Yeah, thank you.
I know I've made my imprint. I don't know if it's been positive or not.
Definitely positive.
But again, as I said, a lot of my job these days is outreach. This is the first time I've been on hard money in my life. So if you have something, you're putting together a symposium or something, reach out to me and I'd be happy to come and talk. All you have to do is pay for me to stay and buy me a beer. All right, thanks everyone.